Welcome to Methods in Biostatistics. Today, we are going to explore a fundamental concept called the standard error. If you have ever wondered how scientists can confidently make claims about an entire population by only looking at a small sample, you are in the right place. This concept is the bridge between the data we can actually collect and the hidden truths of the natural world. Let us dive in and uncover how it works. To start, imagine you want to know the average weight of all adult penguins in Antarctica. It is physically impossible to catch and weigh every single one. Instead, you catch a random sample of 50 penguins and find their average weight. Now, if your friend catches a completely different random sample of 50 penguins, their average weight will probably be slightly different from yours. This natural, unavoidable variation between different sample averages is exactly what we are trying to understand today. The standard error is a magical number that tells us exactly how much these sample averages are expected to bounce around. It helps us understand how close our single sample's average is likely to be to the true, hidden average of the entire population. Now that we have an intuitive feel for the concept, let us look at its formal definition. In biostatistics, the standard error, often specifically called the standard error of the mean, is formally defined as the standard deviation of the sampling distribution of the sample mean. Let us break that technical mouthful down into simple, digestible pieces. When you take many different samples from a population and calculate the mean for each one, those means form their own distribution, which is called a sampling distribution. The standard error is simply the standard deviation, or the average spread, of this new distribution of means. It mathematically quantifies the precision of your sample mean as an estimate of the true population mean. A smaller standard error means your sample mean is a highly accurate reflection of the real population, while a larger one indicates high uncertainty. Understanding this definition naturally leads us to ask why this concept matters so much in real life and scientific research. In biology and medicine, we almost never have access to the entire population, like every single patient with a specific disease in the world. We are forced to make life-saving decisions based on small samples of data collected in clinical trials. If we did not have the standard error, we would have no way of knowing if our sample's average was a lucky fluke or a highly reliable estimate. It forms the absolute foundation for calculating confidence intervals, which give us a safe range where the true population average likely lives. Furthermore, it is the core engine behind hypothesis testing, allowing researchers to prove whether a new drug actually works or if the observed results were just due to random chance. Now that we understand what it is and why we need it, let us look at how to calculate it. The formula for the standard error is beautifully simple but incredibly powerful. It equals S divided by the square root of n. Let us carefully unpack every single symbol in this highly useful formula. The symbol SE stands for the standard error of the mean, which is the uncertainty we are trying to calculate. The letter S represents the standard deviation of your specific sample, which tells you how spread out the individual data points are from each other. Finally, the letter N represents the sample size, which is the total number of individuals or items you actually measured in your study. The formula is telling us in plain English that the uncertainty of our average depends on two things: how messy the original data is and how many people we measured. If the sample standard deviation increases, the data is more chaotic, so the standard error increases. Conversely, if the sample size increases, we are dividing by a larger number, which forces the standard error to decrease, meaning our estimate becomes much more precise. Before we move on, Let us see this with a concrete example. A cardiologist wants to estimate the average resting heart rate of patients at her hospital. She takes a random sample of 36 patients. She finds that the sample standard deviation of their heart rates is 12 beats per minute. We need to calculate the standard error of the mean. To solve this problem, we need to figure out how much uncertainty exists in her sample average. We will use the standard error formula because it directly relates the sample's internal spread to the reliability of the mean. We substitute the sample standard deviation of 12 into the numerator and the sample size of 36 into the denominator under the square root. The square root of 36 is exactly 6. Dividing 12 by 6 gives us a final standard error of 2 beats per minute. This tells her that her sample mean is a fairly precise estimate of the true population mean, typically straying by only about 2 beats per minute. Having seen how to calculate the error once, let us look at another example to understand the power of increasing sample size. A botanist is measuring the heights of a specific species of medicinal plant. In his first study, he measures 25 plants and finds a standard deviation of 15 centimeters. We want to find the baseline uncertainty for this smaller study. We plug in 15 for the standard deviation and 25 for the sample size. The square root of 25 is 5. Dividing 15 by 5 gives us a standard error of 3 centimeters. This represents how much the sample mean would fluctuate if he only measured 25 plants at a time. Now let us see what happens when the botanist wants to be more precise in his second study. He measures 100 plants, assuming the standard deviation remains 15 centimeters. We will use the same formula, keeping the numerator constant while changing the denominator. We substitute 15 for the standard deviation and 100 for the new sample size. The square root of 100 is 10. Dividing 15 by 10 gives us a new standard error of 1.5 centimeters. Notice how the numerator stayed exactly the same while the denominator grew larger. This mathematical shift is what causes the overall error to shrink. His second estimate is now twice as reliable as his first one. These two botanist studies perfectly demonstrate a fundamental rule of experimental design. So let us prove mathematically why quadrupling the sample size cuts the error in half. We are setting out to establish the exact relationship between a multiplier on the sample size and the resulting standard error. We start by defining our initial state. Let the first standard error be SE1, which equals S divided by the square root of n. Now, suppose we multiply our sample size by 4. Our new standard error, SE2, will be S divided by the square root of 4 times n. This setup is the crucial first step. We have translated the physical action of collecting 4 times as much data into a strict mathematical expression. In the next slide, we will simplify this to see the final effect. Continuing from our setup, we now simplify the denominator of our new equation. By the properties of square roots, the square root of 4 times n can be split into the square root of 4 multiplied by the square root of n. Since the square root of 4 is exactly 2, we can pull that 2 out to the front of the denominator. We can then factor out the fraction 1/2, leaving us with 1/2 multiplied by s over the square root of n. But wait, s over the square root of n is exactly our original formula for SE1. Therefore, SE2 equals exactly 1/2 of SE1. We have mathematically proven that to have your uncertainty, you must multiply your sample size by 4. This happens entirely because of the square root in the denominator. So we have proven how sample size affects our error. This brings us to a visual representation of everything we have discussed. On the screen, you are looking at a comparison between two distinct bell curves. The wider, flatter curve represents the population distribution. Its spread is measured by the standard deviation, S, showing how individual data points vary. Inside it, you see a much narrower, taller bell curve. This is the sampling distribution of the mean. Its spread is measured by the standard error, SE. Notice how the arrows clearly show that the spread of the sampling distribution is much smaller than the spread of the population distribution. This diagram beautifully illustrates that while individuals might vary wildly, the average of a sample is much more stable and predictable, clustering tightly around the true population value. Now that we have visualized the distributions, let us summarize the most important ideas from this topic. First, the standard error is your ultimate tool for measuring the reliability of a sample mean. Second, it is crucial to distinguish it from the standard deviation. While the standard deviation tells you about the messy variation of individual data points, the standard error tells you about the precision of your calculated average. Whenever you read a scientific paper and see a plus or minus value next to an average, you are looking at the standard error in action. Finally, always remember the golden rule of experimental design. You can shrink this error and boost your confidence simply by collecting more data and increasing your sample size. You have now mastered the fundamentals of the standard error.